So quick recap of last time. So in earlier lectures, we argued that we should be able to build the whole package of a TQFT from field functors f sub k, where this goes from manifolds of dimension k into set, just for k less than or equal to n. And a local relation u of ball with some boundary conditions contained in linear combinations of fields of n ball with boundary conditions. And so from this, we want to construct invariants of manifolds of all dimensions 0 through at least n. And then ideally, we would also get invariants of n plus 1 manifolds, but we find that we need a few additional assumptions on the starting data in order for that to work. And so why don't I just make those assumptions on the starting data right from the get-go? Because there's lots of interesting examples where there's no possible way to get the n plus 1 dimensional invariance going, but everything else works fine and it's interesting. And we also mentioned in previous lectures that for the 0 through n-dimensional parts of the package, things work in a kind of canonical way. We don't have to choose cell decompositions over manifolds or anything like that. We get things that are manifestly invariant without doing any combinatorial checking. But for the n plus 1 dimensional part, we'll find that we will need to engage in a little bit of cut and paste combinatorics. Okay, so what do we expect from the n plus 1 dimensional part of the TQFT? Well, for all n plus 1 manifolds W, we want a path integral, which we can think of in various ways, and one of the ways we can think of it is a function from the scheme module associated to the boundary of our n plus 1 manifold to the complex numbers. Another way of writing that is z of W, i's and z of boundary W. This is just the dual scheme module. And for all the n-dimensional manifolds, we've already constructed a vector space. It's something we talked about earlier. But now we want to turn it into an inner product space. So we need these family of inner products. And just to make life simple, I want to assume that these are non-degenerate inner products and positive definite, or at least definite. There's some examples where funny signs crop up and sometimes they're negative definite. But let me not worry about that for now. So let's just say positive definite inner product. So that's the kind of the data we expect for n plus 1 manifolds and some extra data for n manifolds. And then we expect a gluing formula. And that's what I'm explaining here. It looks a little complicated, but it's actually sort of the only reasonable thing you can write down. And I've written it in this maybe more cumbersome form because this is the form that's convenient for doing computations. So what does it say? We've got a glued up n plus 1 manifold W, so GL, obtained from this cut open manifold W, and we want to take the path integral of the glued up manifold and express it in terms of the path integral of the cut manifold. So the path integral is a function, so how do we evaluate that on some kind of fields on the boundary of the glued up manifold? Well, we can try to evaluate the path integral of the cut manifold on the cut open boundary conditions. This part of the boundary here and here, but that doesn't make sense because we need something on the entirety of the boundary of W, and we've got 2 copies of this n manifold M. So what we do is we find some orthogonal basis of the scheme module for that manifold M, and we sum over that basis of plugging in these, these EIs kind of go here and here. And then we have to normalize by 1 over the, I'm not assuming it's convenient not to make this into an orthonormal basis, so we divide by 1 over the norm. And this is really just means that instead of taking the inner product in A, we're taking the dual inner product in the dual space Z. If I wanted to write this more cleanly, I would do it that way, but when it comes to actually apply this formula, it's convenient this way. And then finally, these inner products are in fact expressible in terms of the path integral if I take x and y, which are fields on M, and want to evaluate the inner product, I can take the path integral of M cross I and M plus 1 manifold, and this, recall my convention that almost always when I write M cross I, I mean pinched along the boundary, so that the boundary of M cross I is 2 copies of M and nothing else. And so I put X, or maybe some dual, reverse the arrows version of X on the bottom and 1 on the top. Okay, so now the...
So in that presentation, why do you prefer to say that we're asking for 2 things, Z for N plus 1 manifolds and an inner product, and then have axioms that tie them together, rather than just mention at the end of the day that you can think of...
Well, that's what I tried it yesterday, and I got... because it's a little... this... Someone asked you yesterday, what's the data and what's the conditions?
Yeah.
And I don't know, it just seemed a little...
Okay.
It's a good question. Sometimes I do it that way. But,
okay.
Okay, so notice that, so what's one of the things that is implied by this, if we take this formula in the special case of taking M cross, say M is a closed manifold, or even with boundary, M cross I, and then constructing S1 cross I, we would find one consequence of this is that Z of S1, let's say it's closed, is equal to the dimension of M. So if this, these better be finite dimensional. That's one thing that's implied by this. And similarly, if we have a boundary condition, and then we're assuming positive definite inner products on all these spaces. So in particular, we better have positive definite inner products for the simplest manifold with n ball. And so the theorem says that those 2 are sufficient. We've got that, then everything else follows more or less uniquely. So let's state the theorem. And this is our big important theorem that will reproduce all these state sum type formulas from 80s and early 90s. So we fix F fields and local relations, let little z in the plus k module of the boundary plus 1 ball. Be such that the inner product is this is for x and y and so we want this to be positive, definite for all boundary conditions C. Assume also that for any n manifold, dimensional, then there exists a unique path integral, and by path integral I mean this stuff over here, with the path integral of the n plus 1 ball equal to z. So in other words, if if you tell me what the path integral of the n+1 ball is, and if it's compatible in the sense that it gives positive definite inner products here, and if in addition we know somehow that these spaces are always finite dimensional, then everything else works. And we might, in some ways, this is a little unsatisfactory because this condition is somehow non-local. Considering all possible in manifolds, we might like to just have some, we think of the whole theory in some sense as being generated by this n category that we associate to a point. And we would like maybe some condition only on that n category. And that's good, but in practice, it's very often easy to verify this condition. So even though theoretically it might be a little dissatisfied, in practice this works pretty well. So the other thing we talked about last time, and this time I think for most of you guys, I don't need to repeat it, is these sort of planar algebra type diagrams or tensor category pictures, because we're going to use those, we're going to illustrate the proof of this for n equals 2. We want to be able to draw those things. And yeah, maybe in the interest of time, I'm not, I'll recall facts about that as needed, but you should certainly speak up if I'm drawing some kind of squiggly surface picture that doesn't make sense to you. I'm happy to explain it, but I think we've got a different mix of the audience now, so we talked about that some last time. Okay, so let's think about the n equals 2 case, and let's try to maybe somehow prove the uniqueness part, at least in an informal way. In other words, just starting with only this little z, we're going to try to compute the path integral and inner products for as many manifolds as we can. And then after we're done, we'll have to show that what we compute didn't depend on choices we made along the way. So in the n equals 2, I'm going to assume that the dimension of the same module for the 2-sphere is equal to 1, which it is usually in people's favorite examples. And that just means if I have some kind of stringy type picture, I can evaluate it to a scalar if there's nothing on the outside. That's typically the case. And in fact, in most of our sort of built-in let me say it this way. In particular, I'll also assume that this with empty boundary conditions is one-dimensional. And in fact, it's got a preferred basis element. We've got sitting aside here is the empty set for D2. I'm going to use empty pictures on many different manifolds, so I have to give a subscript to remind me where the empty picture is living. And that sort of gives us a standard evaluation. So a standard way to evaluate pictures, we just see for a picture in the disk. And of course, any picture on the 2-sphere can be turned into a picture on the disk. It's just some multiple of that, and that gives us some number. So I'm going to refer to that as a standard evaluation. And for those of you familiar with things, it's a familiar object, and then I wanted that little z equal to some lambda times standard evaluation for lambda in complex numbers. Turns out lambda is not going to matter a whole lot, but when we do this in 4 dimensions instead of 3, it will be important to have this at our disposal. So, so we know, so we need a path integral for just a union of a bunch of 3 balls. And we can just take this to be v of the 3-ball insert the cell a bunch of times. we already know this. It's just, so for the simplest, for three manifolds of this form, we know the path integral. Step 0a. Step 0b is that we have the inner product on scheme model of the straight moving of a bunch of three balls. Two balls, excuse me. So we just apply this formula here. So we've, and let me introduce some terminology I'll call so K comma L body is going to be K manifold composed of 0 through L intervals. So here we've done the case of a 3, 0, and 2, 0, and we're going to sort of induct them on the cell. So the next thing we might want to compute is the path integral of something consisting of a 0 and 1 handle, for example, E2 plus S1. And so now we can apply this formula because we can think of B2 cross S1 is obtained from B2 cross I by gluing things together there. So first we have to decide what we want to evaluate it on. So let's say I just have a number of parallel strands. Labels A, B, C, something like that. Actually, let me, I think I want to consider just two cases. I want to consider two parallel strands with opposite orientations with labels A and B, and I want A and B to be sort of minimal item movements that I talked about last time, so simple objects. So union B. Okay, so when we apply this formula, we have to sum over an orthogonal basis of the vector space associated to this cut thing. So what is the cut thing? It's a disk. So if I zoom in right here, I see a disk and I see sort of an incoming arrow labeled by A and an outgoing labeled by B. And it's, because these are minimal item posits, that's going to be 0 dimensional unless A is equal to B. So this is equal to 0. A is not equal to B. And if they're equal to each other, this is a one-dimensional space. If A and B equal, and it's generated by just a single strand there. So I need to know what's the inner product of the strand. So we go back to the inner product formula here. Applying this, we see that the inner product of a strand labeled by A with itself is the inner product inside the scheme model of two ball boundary conditions. That's going to be equal to, well, we glue the two things up, we just get a loop. And we just evaluate that loop and we multiply by lambda. So this is lambda times, let's call it loops a day. So now that we know the inner product, we know what our orthogonal basis is, we know this inner product, so we find that this will work out to be, so let's write it out, z of 2 cross I, evaluated on the loop labeled by A, times 1 over this factor here, and loops of A. But this is also just lambda loops of A, so this is simply 1. So this is in the case that. And similarly, we could compute the path integral for B2 cross S1 with any boundary conditions, but in the future, this is all we would need. So the next thing we want is step 1A.
So you're assuming that F and U are like, or F is like defined using these kinds of things?
Yeah, that's right. It's the example I was talking about yesterday.
Okay, so you're just doing that one example.
Yeah, right. I guess I should have made. So what I'm going to do is I'm going to talk about things just in that one example. Then we'll take a step back and realize that what we did would work, much more widely. But to make things concrete, I'm going to do that one example. Also, at the end of the day, hopefully at the end of the next hour, we'll have written down those derived Vero states and formula, and that is specific to just these sorts of pictures. Well, I guess implicitly I've assumed that I only have a single region color here for simplicity, but this can be modified.
I mean, that's just that dimension is 1 rather than just some finite number.
Well, you could have this be one-dimensional, but still be multiple colors possible.
Okay,
sure. Okay, the next thing we want to compute is, so what's the next, after a wall, what's the next simplest connected two-manifold? It's an annulus. So we want compute the inner product on A of S1 plus I. Some kind of boundary conditions. So the only boundary conditions I'm going to consider are the empty boundary conditions. That's all we'll need. So what's the base? What's the basis of this space? When we talked about the spine theorem last time, if I have void spaces are premium here because I'm going to want to keep all these things on the board and maybe this too. So an easy special case of the spine theorem that we talked about last time is if I have an annulus with nothing on the boundary, where the whole thing collapses to the central core, and that means that a basis for the scheme module is just loops labeled by A. Right? Again, A lies in our collection of simple objects we talked about last time. So what we want to compute then is the, I'll call that little l sub A. And we want to compute the inner product of little l sub A, little l sub B, and that, applying the bottom formula over there, is path integral of S1 cross I, evaluated on little l sub A bar, little l sub B. But S1 cross I is just B2 cross S1. That's the thing we just did. And either made, strangely enough, we computed exactly the case we need. So if A and B are equal to 0, we get 0. I mean, if A is not equal to B, we get 0. is equal to B, we get 1. So this is just equal to delta AB. So in other words, these L sub A is forming not just an orthogonal, but an orthonormal basis of scheme logic for S1 cross I. So next, now we want to compute another 3-manifold. And I should say, at this stage, if we wanted to, we could consider this. I want to actually do this, but suppose we wanted to compute, say, a general 0 and 1 handle on this 3-dimensional. So I have sort of a solid. I have this thing, not 2-dimensional, but 3-dimensional. Well, I could cut it along these curves, and after I'm cut, I'm left with a 3-ball. I know how to compute the path integral of the 3-ball, and then when I do these things together, I'm needing to take these inner products on disk, and I already know that. So using similar techniques, we could compute any 3-manifold like this with arbitrary boundary conditions. Okay, so what's a 3-manifold that's more complicated than that? Well, the simplest one that's not in our list of things we've computed so far is S2 cross I. So we now would like to compute the path integral of S2 cross I. We need to evaluate it on some picture on the 2-sphere. And by assumption, every picture on the 2-sphere is some multiple of the empty picture on the 2-sphere. So we really just need to evaluate this on the empty set. That's two of them, because we've got 2 boundary components. So we can take, here's my attempt to draw this 2 cross I, it's this shell sort of thing, and we can cut it along this annulus in the middle. So it's equal to lower piece and an upper piece. Northern hemisphere cross I and southern hemisphere cross I. These pieces of the boundary that are on the 2 spheres, those are all empty. And so we just have to sum over a basis of this annulus here. This part of our formula. We just got done computing an orthonormal basis for that. So we see that this is equal to the sum over all our simple objects for our category of the path integral of E2 cross I. Say this is the let me just write, I guess the cut open manifold is 2 copies of E2 cross I. And then we're evaluating it on L sub A bar and L sub A here. And then we should divide by 1 over the norm square, but this turns out to be wrong, so we can just leave that off. And then this should be multiplicative, so what we really have is just for one of these pieces we'll give the loop value at A times lambda, and then that happens twice, so it's sum of lambda squared. So this part, if we leave off the lambda, this is a familiar quantity. It's like the sum of the squares of the quantum dimension. So we're seeing that sort of ubiquitous number is popping up quite naturally here. So almost done. I guess we need to compute the inner product on the scaling module of the two-sphere. Well, the scaling module of the two-sphere is one-dimensional, and its basis element, our preferred basis element is the empty picture, so we want to know what is the inner product of the empty picture on S2 with itself and the value of S2. And that's what we just did. We take, according to the bottom formula, S2 cross I, we put empty pictures above and below, and it comes out to be this. So the inner product of the empty picture with itself is and the square of the d values. Finally, so now, actually, so there's one other case I left off here that I need for this inner product on two balls. You might want to consider the case where you have only one disk or two ball, the inner product of a picture like this. So I've got sort of labels A, B, C, and then maybe I've got this dot in the middle that has something alpha with itself say. And what's that equal to? Well, it's equal to lambda times standard evaluation of, we sort of glue these two trivalent things together and we get a picture that looks like this. ABC. And well, what is that? Well, it's just some number. I mean, this is one of the sort of basic constants that determines our theory. So we can't evaluate in terms of something else, but typically if you know some particular example of fields like this, you'll know these things. So I'm just going to take some notation to that. I'm going to call it theta, because the graph looks like theta, so A, B, C, alpha. Okay.
I mean, you should presumably still have a lambda in that formula. Because
oh, yeah, right.
If they just part of the underlying category.
Okay, so at this point, we've done enough that we can find a formula for a general three-manifold, because we know how to, if we want to attach a one handle, we know how to do that, because we know inner products on two balls. If we want to attach a two handle, we know how to do that, because of attaching for two handles and annulus. And if we want to attach a three handle, that will be the attachment region of the two spheres. So if we have an explicit handle decomposition of our three-manifold, we can write down an explicit formula for the path of this. So let's do that. And after we do that, then we want to talk about showing that you get well-defined invariants for a three-manifold. So the three-manifold, and I want to consider, I'll call M0 just the zero handles. Does everyone know what I mean when I say handles for a three-manifold? Which is contained in M1, which is the 0 and 1 handles. M2, M63, this all in. Okay, so in writing formulas like this, it's useful to sort of start at the top and work our way down. So we know that Z of M, a full manifold, and for convenience, I'm going to assume it's closed. Z of M is equal to Z of M2 union all the three handles. So if we were to apply, so this is, again, over and over again, we're looking at a n+1 manifold cut somehow, and this time we're cutting it into a sort of neighborhood of the 2 skeleton and a bunch of 3 balls. So applying this formula, we see that that's equal to, well, what the manifold we're attaching along is a disjoint union of a bunch of 2 spheres. And the 2 spheres all have one-dimensional spanning spaces, so there's really no sum here. So it's equal to Z of M2 evaluated on the empty picture. And we should also have all the 3 handles evaluated on the empty picture, and that's gonna, each of those is gonna give a factor of lambda, because the empty picture evaluates the 1, and then our official thing is lambda times that. So we get lambda to the number of 3 handles. And then we also have to, we have a term like this for each 3 handle. So that's 1 over lambda squared. Call this capital D squared is the usual thing, right? So this is my definite, so I don't have to keep writing that. Oh, this also is 3 handles. Okay, so if we can compute the path integral of just the M sub 2, the neighborhood of the 2 handles, we know how to do the rest. We just add this factor, 3 handles. So similarly, Z of M sub 2 is equal to Z of M sub 1 union all the 2 handles. Again, we have a manifold split into pieces. What's the thing we're gluing on? What would M be in this picture? Well, each 2 handle is here's my 2 handle. 2 cross I, and I go and I try to attach it to here's my picture of M1, and this annulus here is going to attach to some annulus here. So I just think on M1 I have a bunch of annuli that I'm going to attach 2 handles along. So this is going to be equal to, this time we are going to have to take a sum. What's the sum going to be? Well, for a single 2 handle, we'd have to have all possible labelings of this by simple objects, minimal idempotency of our theory. And we need that for each. So we're going to be summing overall labelings of 2 handles by simple objects. Okay, and then for each such labeling, we have Z, so let's call this beta sub 2. So a set of all labelings, all such labelings. And Z of M1 evaluated on, I don't know, what, L sub, this is my beta. L sub beta. So L sub beta is my shorthand for a bunch of loops, 1 for each 2 handle, each of them labeled according to this. So it would be this and a bunch more. Okay, so then we also have the other piece of our cut of a manifold is a bunch of 2 handles like this. Each such 2 handle is going to have some loop like that. That was our orthonormal basis for this. So we're going to get lambda to the number of 2 handles times the product overall two handles of loop value. I'm not sure what the best notation is. Loops of A, where A is the label coming from beta. Maybe I should call it. And beta. So let's let little h H is a particular two handle, and this would be a loop of beta H. So now we've reduced it to evaluating this piece, Z of this one handle body, right, with some curves. Now for simplicity, I'm going to assume that we have a generic handle decomposition, kind of dual to a triangulation. So that means I have here's say in my one handles attaching to a zero handle, and we have a few different ones coming out. So zero handle. And so if it's generic, it means that every zero handle has exactly 4 one handles coming on. Think of it sort of a tetrahedral arrangement, kind of like a foam. And then on each one handle, there are exactly 3 two handles coming on it. Think of 3 foams kind of coming together, sort of Y cross I. So these annuli that we were just talking about, run down 2 handle, and they go off here, along with another one. So it's sort of a tetrahedral arrangement of these annuli on the zero handles. And on the one handle, we just see sort of 3 annuli coming in like this. So, in evaluating this, the labels along these annuli are fixed. Let's see. A, B, and C, where A, B, and C are some labels coming from this beta here. And so what do we have to sum along? We have to sum along labelings of these disks by something like this here. We've got this A, B, and C, and the rows here correspond to these. And when we fix A, B, and C, we need to run through an orthogonal basis of the vector space of the disk with those 3 points. So sum over labelings of the one handles. Now strictly speaking, so I think I actually want to take a shortcut here. We would have like a different label here and below. But then when we went to evaluate the one handle, if they didn't match up, we would get 0 because we're choosing an orthogonal basis. So one way to shorten and not have to mess with that is, say, instead of cutting here and here, that's kind of redundant. Why don't we just cut in the middle of each one handle? And then we just have a single thing. So let's write this as, well, I'm taking a few shortcuts here. I'll leave it as an exercise for you to make sure I didn't cheat or something. So I'm just writing, what I'm going to do is I'm going to write in one, neighborhood 1 scan is actually just a union of a bunch of 3 balls. Each 3 ball is a 0 handle plus half of each one handle that comes into it. So it's a sort of caltrops shaped thing.
Sea urchin.
Say what?
Sea urchin.
Sea urchin? Okay. A very balding sea urchin.
So this is jumping ahead a little bit, but how expensive is this decision to only look at generic handles when we finally come to checking independence of the...
When we check independence, we're actually this is sort of a tangent. We want when we check independence, we're not going to use this formula. We'll be back in the general case. So, you could do the. We could just finish the. I mean, of course, in higher dimensions, we're not going to write down something like this. So, okay, so the sum over labelings of the one handles by this little trigonal thing here. So, and so the pieces are going to be product over the one handles of this lambda times some theta, so ABC alpha, something like that, something like this. And then we're also going to have a product over the zero handles. So the zero handle we have, what's left over is this sort of tetrahedral picture. What does it look like? A, B, C, D, E, F, alpha 2, alpha 3, alpha 4. And it turns out, so that's some big complicated number that depends on 6 of our minimal idempotents and 4 of these vertex labels. But this is, it's a complicated function, but you can look up in the literature what these are for particular theories. And this is, again, just one of the sort of fundamental structure constants of the theory. They're sometimes called 6J symbols or decoupling coefficients. So I'll just write it as tetrahedral symbol of ABC. Okay, so now combining these, so now we're done. So we just have to sort of combine these and write one giant formula. So we get finally the Z of this, our general 3-manifold is equal to the sum labelings of the 2 handles by minimal idempotents. And then once we have that, we take the sum over the labelings of the 1 handles by basis of the ABCs, things that live there. And for each such sum, labeling of the 1 and 2 handles, we take the product over the 3 handles of this term. So that's 1 over d squared times the product of the 2 handles of lambda times groups of A. Of course, A depends on the labeling. It's the product over the 1 handles of this goes in the denominator. So this theta was an inner product of things, and this inner product we have to go inverse this of ABC alpha inverse, and finally the product of the 0 handles of a tetrahedral arrangement like this here. So if our three manifold's closed, so we ask, what's the
Oh,
overall
so-
factor of lambda, and it's the Euler's
That factor of lambda wasn't in this last formula. Is that a problem?
So as you may have noticed, the power of lambda we get for any manifold with boundary and knot is just the Euler characteristic of a manifold. And for these particular derived Euro theories, there's no strong reason to leave it in. So if you want, just ignore the lambdas. Anyway, so this is the celebrated derived Euro state sum formula. I think Tarayev and Vero just did it in the case of temporally leave or SU2, where you can ignore the second summation. It turns out there's always these, for that particular example, these spaces are one-dimensional and there's a preferred basis element, so they left out that piece. But it's actually, it's a very general, we sort of started with a very generic two-category or planar algebra to drive a formula like this. And using the same techniques, we could write down something for a non-generic cell decomposition. It wasn't anything that forced us to do that. We would just have these pieces that figure in here. Instead of being tetrahedron, it would be some more complicated graph depending on the link of the vertices. Here, instead of a theta symbol, you might get some kind of generalized theta symbol that looks like that, depending on how many two handles are going over each one handle. You could also be you could get a version if we had different region colors, like if we were in a cell-factor planar algebra with black and white shadings. We'd have to decide for each empty picture whether it's a black empty picture or a white empty picture. And then depending on the colors of those empty pictures are these sort of simple objects that are going to be indexed by the thing on the right and left, but it works in that case too. Okay, so now, for the first time, of course, we've made contact with the usual TQFT literature. But we still haven't shown that this is well defined, that this is independent of the handle decomposition. So what Tarayev and Vero did was they just took this as sort of an ansatz. They said, okay, we bet this is an invariant of three manifold, and then they showed, and then they took a dual version for a triangulation. And they show if you manipulate the triangulation, there's a sort of finite set of moves you can, ways of modifying your triangulation where you get between any two, and they, by some complicated identities involving these tetrahedral symbols, they showed it was invariant. So we're not going to do that. We're going to find a subgroup proof. So what is it? Let's think about, so now,
So this thing is a number?
for closed three manifolds, a number. Again, there's a version for a three manifold boundary, but we'd have to choose some way of putting a variable or loosening the boundary and extend the decomposition. Let's think about the general case now. So now, forget about n equals 2, we're just doing a general n-dimensional TQFT. What I want to do is okay, so here's our inductive assumption for the general case. So we've got our n plus 1 comma k bodies. These are n plus 1 dimensional manifolds whose composed of handles of index 0 through k. And we have n comma k bodies, n-dimensional manifolds, 0 through k handles, and we're also going to think about n minus 1 bodies. And so let's assume inductively that here we have just the path integral defined. And that this definition does not depend on canceling or sliding the handles. We need to remind people what canceling a handle is or sliding. So the theorem we're using is if we have a manifold composed of various handles, we can get between two of them. Just say, forget out this just restriction of index k for the moment. We can either change the order in which we attach things. We can vary the attachment region by an isotopy. That's sometimes called handle sliding because here's a couple of one handles attached, and then I can kind of do that over there so that it looks like that. Varying this attachment region by an isotopy. And if I say here's two manifolds, and I attach a one handle, and then I attach the two handle here, that's as if I did nothing. So that's called handle cancellation. We can have handles of adjacent indices. So think of it as like Morse critical points. Okay, so those are the sort of combinatorial moves that we're going to have to check in variance number. And so this path integral, I want to not just have it defined, but it's independent of handle cancellation. The independence of sliding, just the way we define things, is going to be, that's sort of automatic for us. The only thing we need to check is that for an n-dimensional body, we've already got a vector space that's well defined, independent of the handle decomposition. But we want to say that the inner product that we define is independent of cancellations. And then for our n-1 manifold, we define categories. And so there's no new structure to check, but what we do want to check, which wasn't part of our initial assumptions in the theorem, is that this is semi-simple. With finitely many idempotencies. Okay. So when k equals 0, that's getting deduction started, all these are fine. There's really nothing much to check.
So sorry. You're going to prove these three things at once. Or you're going to prove these three things for each k by inducting on k.
Yes.
So what is k?
K is the maximum index of the handle. So this is handles of index 0 to k.
The n plus 1 and the n.
That's just the dimension of the manifold. So we're going to be thinking about the manifolds of dimension n plus 1 and n minus 1. You think of, if we're gluing n plus 1 manifolds with corners, then we've got the n-dimensional manifold that we're gluing along and the n minus 1 dimensional corner. We have to think about all those things. So, okay. So which of these we want to attack first? Well, one, we notice that this assumption implies this one because the inner product we just defined in terms of m cross I, and m cross I just has a thickened up handle decomposition. So if we have a well-defined invariant of n plus 1 manifolds, that will give us so this is nothing extra to check. So now let's think about proving hand. Oh, and then in terms of coming up with this Z before we show it's well defined, that's just the procedure we went through here. We showed, we started out with just these, zero handle things, and then that gave us an inner product, and then we could define this here. Well, I think it should be clear that the procedure we went through here works in arbitrary dimensions. It's just the fact that if you've got a ball across a sphere of a certain dimension, you can cut it into two balls and they're gluing along a sphere of a lower dimension. In fact, it's moved from here one sphere to a zero sphere, or a two sphere to a one sphere. That's the inductive step. So, how do we prove handle cancellation? Let's picture it now. So handle H, sorry, K handle. This one handle here is a K handle. So the rest of W. So this is maybe a close-up of, so we're in the process of trying to define the path integral for n+1 manifolds composed of 0 through K handles. And we can write something down because in order to write down the gluing form, we already did the K minus 1 handles by induction. For the K handles, we just need to know the inner product over this sort of attaching region, but that attaching region is handle that's K minus 1. So that's something we did before. Just like each step here, the thing we needed to know was in the line above. But we don't know that it's well defined. And so to show that it's well defined, we have to show some variant under cancellations. And a cancellation looks like this. So at step 0, we have our manifold. At step 1, we add the K minus 1 handle. And at step 2, we add the canceling K handle. And the result is just if we did nothing. This is a product. But suppose we switch the order. Suppose we first attached this K handle. It's not really K handle anymore. We glue that blob on. And then we glue the K minus 1 blob on. Then each time we're really just attaching a boundary collar. So from the point of view of it, attaching this K handle, I guess in this case it's a literal picture for n+1 is equal to 2. This disk relative to this edge is just a product. And this thing also relative to an edge there is just a product. And that's true in general higher dimensions. And it's just one feature of our gluing formula. I guess I erased it, but by the way we define the inner product, if we're just gluing M cross I onto the boundary of W, it's sort of automatic in our gluing formulas that doesn't change anything. So if our gluing formula was associative somehow, if it was such that we got the same answer no matter which order we glue things, we're done. So that's the core of the argument. But it's not immediately obvious that that's true. So that's the lemma we're going to have to prove, and I think I might postpone it to next time. But let's just see how the rest of the argument goes. How are we going to prove inductively that these things are semi-simple with finite limiting idempotence? Well, this part of the semi-simplicity comes from the fact that we've got these inner products that positive definite inner products allow us to take orthogonal complements. And so a standard way of proving that something is semi-simple is to show that a metric is preserved. So what's left is the thing with finite limiting idempotence. And that, maybe I'll postpone that to next time too, because it's kind of wrapped up in the way we prove this. So when proving this gluing formula, we have to sort of think about reversing. We're going to have to think of the idempotence on this corner here, where all three of the people, we've got 3 different manifolds, and they meet along this n minus 1 manifold. And knowing the idempotence and the inner products is going to figure into joint associativity. Okay, once we do that, we still aren't quite done. So if we get these inductive steps, and we prove this lemma, and similarly the thing for verifying that we're finite limiting idempotence. Actually, maybe that's, come to think of it, since I'm assuming maybe we don't need that because we saw earlier that if we had a finite path interval, that implied that these vector spaces are finite dimensional by just crossing with a circle. Similarly, if we have an n-1 manifold, we can cross with a circle, and then we get some vector space, and that vector space is, once we know semi-simple, it's got the normal basis given by the idempotency. So the finite dimensionality here implies finite idempotency here.
No, just a second. I mean,
for example, if you've got an infinite depth, that's subfactor, so the rectangular category.
it sounded like you were implicitly saying that finite dimensional algebra is automatically semi-simple.
No. Finite. I'm saying that algebras whose zeroth Hochschild homology is finite dimensional have finitely many minimal idempotencies. That's basically what I'm saying.
Where did you get semi-simplicity
From the inner products that we got here. So once we prove semi-simplicity, okay, maybe I shouldn't cross it out. Yeah, there is something to check because our inductive assumption, the theorem that I erased, didn't say anything about these categories for n-1 manifolds. We just talked about inner products on the disk and finite dimensionality. And then we bootstrap our way up to much larger implications. So once we run through this argument, we have a well-defined path integral for any n+1 manifold and well-defined inner products, but we haven't actually proved the general gluing theorem because so far we've only been gluing one handle at a time. And suppose we just wanted to do two random manifolds along some random, two random n+1 manifolds along a random n manifold. How do we know that gluing formula works there? So here's n1, w1, w2, and the things we choose some handle decomposition down here, and then a sort of compatible handle decomposition down here, and once we know that we can, for the glued up manifold, choose any handle decomposition we want, and we choose a special one that's compatible to gluing. So that's.
I think that's again using the as yet unproved associativity of the gluing formula.
Right. Yep. So what I'm trying to do is finish the entire proof except for this, slightly technical limit about the associativity of gluing formula, and then prove that next time. So let's take a step back and so what's the point of all this, or how does it compare with other approaches? So, giving a preview of what's to come, we came up with this sort of general technique. I illustrated it in n equals 2, but it's going to work any dimension for any set of fields as long as we have this finite dimensionality and so on. Of cutting manifolds up into handles and then writing something down. So we'll see in dimensions both lower and higher dimensions, we'll be able to get formulas similar to this one. And most of those formulas, in fact, maybe all of those formulas, existed in the literature, 15 or 20 years ago. So we might think it's disappointing. We haven't really discovered anything super new, but the proofs are new because in the literature, people have used various ad hoc techniques to show that this thing they write down is independent of the handle thing. And we just prove this associativity of gluing, which is, I said it was technical, but it's not so hard. We prove this once and for all. And so that means for all these examples and any future ones we dream up, we already know some independence of handles. So we've no more. We did have to check some combinatorial lemma, but we did it in a very general way. We don't have to keep doing it over and over again. So there's sort of three main cases of this to talk about. In the future, one is for n equals 1. And that would just be vector spaces for circles and intervals and path integrals for two manifolds, and then we get the familiar classification of 1+1 dimensional TKTs in terms of for being assigned with. We also want to look at this in the braided case, so we'll be drawing these sort of loop pictures, except we'll be drawing them in 3 space, and that's where the Reshetikhin Terayev and Calcium Craniot or type invariants will come in. And then finally, we'll look at it in the case of these finite group examples for digraph field theory, and we'll also derive the sort of digraph, discrete sum over flat bundle type connection. So that's it. So, and it's going to continue to be 11 o'clock on Monday, 10 o'clock on Tuesday.